Hello, today's video is about our latest paper, Diagnosis and Prediction of IIGPS countries' bubble crashes during Brexit. This is Bikramaditya Ghosh from Bangalore. I am a researcher predominantly in the risk management space, considering financial analytics and various financial econometrics tools. In this research, there were some international researchers who were with me, and together we have developed this particular paper, which got published in the journal Mathematics, which is by MDPI, and at the same time, our paper covered the troubled European economies, which are known as IIGPS. Some people call them gypsy, some people call them pigs, but we decided that those names are derogatory in nature, hence, we would rather call them IIGPS. It's a neutral coining of a name for a troubled European economic bloc with Ireland, Italy, Greece, Spain, and Portugal and Spain. The model that we have used is log periodic power law, which is extensively used by ETH Zurich, the Federal Institute in Zurich, and this came into existence by Professor Didier Sornet of ETH Zurich alongside Professor Andreas Johansson. They, in their 1996 paper, for the first time gave the idea of this name. Since then, this entire concept got evolved, and now they have a financial crash predictor in ETH Zurich. They publish an financial crisis observatory report, which is called FCO Cockpit report, on a monthly basis for troubled economies and troubled economic blocks. Most financial crises are endogenous. They are born out of moral hazard, conflict of interest, and lack of accountability. Positive feedbacks generate bubbles and even sustain the bubbles. Speculative bubbles seen in financial markets have an oscillating movement that can be captured by an equation called log periodic power law. The ending crash of a speculative bubble is ideally the climax of log periodic oscillation. Since it's an econophysics concept, so from the point of view of physics, it's kind of a phase transition when a growth phase is replaced by a phase of deterioration, sudden deterioration, and the entire thing is separated by one particular day we call as TC or T critical. The most important concept in this regard is called drawdown. Drawdown is fundamentally the cumulative loss from one local maxima to the immediate next minima. And ideally, the drawdown has been calculated as 20% and above for the European and American nations by Didier Sornet in his book Why Markets Crash. But we have initially calibrated our work with a stylized fact from our previous paper that drawdown is more than 7%. So we have kept drawdown more than 7%. If we see this particular equation on the top, that signifies the equation of log periodic power law, and we will see something very interesting there, that there is something called A. A is the price at the peak of the bubble. B is the decrease in the log periodic power, means the decrease of the bubble. And TC is the T critical, the critical time after which the crash happens. It's on the top. M or beta, some people call it M, some people call it beta. It is the exponent of the power law growth. Omega is the frequency of log periodic oscillation, and phi is the phase parameter. Now, if we look at the equation which is at the top, this is the original JLS equation or Johansson-Ledoit-Sornet 2001 equation. It has got too many non-linear parameters, so the fitment becomes quite fragile. That is why the equation that has been shown at the bottom has come into existence. This is an equation by Filiminov, Vladimir Filiminov and Didier Sonnet, recalibrated model of 2013. If we notice that model, phi has been replaced and that c has been replaced. So C1 equal to C cos phi and C2 is equal to C sin phi. So by that, C is basically the relative magnitude of fluctuation. So by that, what has happened, the number of linear parameters went up and the number of non-linear parameters were reduced to only three. One is omega, that is the angular frequency of log periodic oscillation. Tc is the critical time, and m or beta, that is the exponent of the power law growth. We got some stylized fact which has emerged out of the 77 crashes during Brexit period in IIGPS countries that we have investigated. So in those 6 years we have investigated approximately 77 crashes across all these 5 IIGPS countries, namely Italy, Ireland, Greece, Portugal and Spain. We got the beta or the m value, which is the exponent of the power law growth, as 0.52 plus minus 0.38. Omega or the angular frequency of the log periodic oscillation, we got about 9.29 plus minus 3.39, and drawdown we got about 7%, and with that we have got an efficiency of almost nearing 95% of prediction. When we further calibrated our model with the help of machine learning, and we recalibrated our model with error correction and back propagation of errors, we ultimately found 100% LPPL footprint among all 77 past crashes in IIGPS stock indices from 2015 to 2020. So LPPL works perfectly well when herding is evident. LPPL fitment shows inconsistency if herding is absent. But thanks to human nature and thanks to the inefficient way most markets operate globally, and most markets deviate from efficient market hypothesis by a large margin. So by the nature of its operation, herding is prevalent. Thus, LPPL works pretty well in most. Here you can see the actual paper in the journal called Mathematics from MDPI Switzerland. It is written by myself, Vikramaditya Ghosh, my Greek counterparts Spyrus Papastaniou and Dimitris Kinorgios, along with my student Nikita Ramchandani. Thank you very much for watching and appreciating our work.